We are currently watching a massive wave of commercial AI study tools flood the education market, all promising to generate instant flashcards, practice exams, and comprehensive quizzes for students on demand. But the mainstream academic debate surrounding these tools is stuck on the surface. We focus heavily on the ethics of AI, the hallucination of facts, and the risks of student plagiarism. For developers and instructional designers, those debates obscure a much deeper mathematical hurdle beneath the surface. That hurdle is pedagogical validity. In this context, validity means asking a precise question. Can a large language model actually output a rigorous analytical exam question that accurately measures human comprehension? We have an educational market saturated with automated assessments, built entirely on a psychometric foundation that remains highly suspect. When developers build these tools, they rely on a standard evaluation method to prove they work, putting the generated questions in front of human expert instructors for a qualitative review. Researchers recently tested this exact method by running a blind survey, pitting human-crafted exam questions directly against questions generated by a vanilla ChatGPT prompt. This bar chart shows the results of that survey. Across 5 separate evaluation metrics, the human experts rated the AI-generated questions as nearly identical in quality to the ones written by actual instructors. Look specifically at the clusters for correctness and adequate complexity. The experts could not tell the difference. They evaluated the bare-bones ChatGPT output as having the same pedagogical value as their own work. Yet this qualitative consensus hides a structural flaw. There is a psychometric gap buried in the data that subjective human eye reviews simply cannot detect. Relying on these qualitative surveys creates an industry-wide illusion of validity, masking deep mathematical failures in how large language models construct assessments. To see where the models fail, we have to isolate the mechanics of an analytical multiple-choice question. Structurally, these questions break down into 3 distinct components: the stem, the correct answer, and the incorrect options, known as foils. The stem establishes the prompt. In an analytical exam, it doesn't ask for basic trivia. It targets a complex, high-level learning objective. The true engineering challenge lies at the bottom of the structure. Providing the correct answer is easy. Crafting the foils is where the assessment actually gains its rigorousness. A valid foil acts as a cognitive filter. It has to accurately measure human misunderstanding. This requires a delicate balance. A foil must be challenging enough to tempt a student holding a genuine misconception, but it cannot be completely irrational or excessively difficult. This exact balance is where an unprompted language model breaks down. It cannot reliably generate these nuanced incorrect assertions on its own. Engineering the perfect distractor is the ultimate test of a model's pedagogical capability. To write a valid incorrect answer, the system has to understand exactly how a human student fails. To measure this failure, researchers apply item response theory, or IRT. This provides a mathematical framework to evaluate the true validity of these foils, completely bypassing human bias. This IRT graph plots 2 main variables. The x-axis tracks the student's latent ability, and the y-axis tracks the probability that they will select a specific incorrect foil. The solid red curve represents the psychometric baseline, a properly balanced foil crafted by a human instructor. The math here tells a clear story. High-ability students on the right rarely select this incorrect option, while lower-ability students on the left are predictably and smoothly drawn to it. Now look at the real-world performance of a foil generated by a vanilla ChatGPT prompt, shown here as the black dashed curve. It shifts drastically to the left and exhibits a much steeper drop-off. This massive mathematical gap reveals a severe flaw in discrimination and difficulty. The steep, left-shifted drop-off means the model's foil is only successfully tricking the absolute lowest ability students. In a real-world testing environment, these distractors are simply too predictably and obviously incorrect to serve as useful analytical hurdles. The root cause of this failure lies within the core architecture of the language model itself. Pre-trained weights are heavily optimized to output highly probable, articulate text. They inherently lack the localized, specialized knowledge of specific cognitive errors made by a given cohort of students. Without the ability to accurately replicate nuanced human misconceptions, a vanilla language model will mathematically fail to produce a psychometrically valid assessment. To fix this, researchers developed a specialized prompting architecture called AnaQuest, designed specifically to close the psychometric gap. AnaQuest alters the generation process by injecting a critical missing ingredient directly into the LLM prompt: formative assessment data. This data isn't abstract. It consists of raw, free text responses written by actual students during open-ended assignments earlier in the semester. The engine issues a highly specific instruction to the model: examine the raw student text, extract the localized misunderstandings, and generate foils that explicitly mirror those real-world errors. When we plot the AnaQuest curve in blue against the original IRT data, the results of this targeted intervention become visible. The blue dashed line slots neatly into the space near the red baseline. By reading the student's mistakes, the generated foils now closely approximate the required difficulty and discrimination levels of human-crafted questions. To confirm this proximity, researchers utilize a rigorous statistical distance metric known as KL divergence. The math confirms the visual. The AnaQuest model's bivariate distribution resembles human foils at nearly 3 times the accuracy of a vanilla ChatGPT prompt. An AI can only generate a valid analytical distractor when it is explicitly grounded in the real, messy data of human misunderstanding. Which brings us back to the central paradox of the blind survey. The vanilla model's output completely failed the rigorous statistical tests, yet the human instructors still rated it as identical to their own work. This exposes a deep cognitive bias in how we review text. Human reviewers naturally default to evaluating the linguistic surface, grammar, and formatting of an answer. Generative AI excels here. It produces highly polished, plausible assertions that pass an expert sniff test, even if the structural reasoning underneath is completely hollow. Articulate text generation is simply not the same thing as true psychometric validity. Qualitative expert surveys are useful for checking grammar and clarity, but they are structurally incapable of measuring the latent validity of an AI assessment. For the engineers and instructional designers building the next generation of automated study tools, this reveals a clear operational mandate. Models cannot operate in a vacuum. Relying on their static, generalized weights will predictably yield generic, ineffective assessments. The required architecture must be a closed loop. Future edtech systems have to be designed to continuously ingest dynamic student state data. Feeding the engine this continuous stream of formative data is the only mathematically proven way to ground the model in the reality of cognitive errors. The engineering goal is to transition the AI from a generalized text generation engine into a highly localized, psychometrically rigorous pedagogical tool. Automated education will reach its absolute full potential when the engineering shifts from simply using AI to replace subject expertise to replicating a teacher's specific understanding of why a student is failing.